Imagine sitting in a crowded cafe, completely unaware that the laws holding your body together are about to fail. You would not hear an explosion, see a flash, or feel even 1 second of pain. Somewhere in deep space, a microscopic bubble of true vacuum could appear from a quantum fluctuation. It would expand so close to the speed of light that no warning could ever reach you first. When it arrived, the chemistry inside your cells would not burn or break in any normal way. It would simply stop being possible. The bonds holding your atoms together would lose the rules that made them stable. Your memories, your body, the floor beneath you, and the planet itself would be rewritten. Then the bubble would keep going. It would swallow Earth, pass through the sun, and spread across the galaxy. This is not a rejected idea from a science fiction movie. It is one of the strangest ways modern physics says the universe might end. And the most disturbing part is that this is only one possible ending. Humanity usually imagines the end of the world as something loud, visible, and close. We picture asteroid impacts, nuclear fire, climate collapse, or the sun expanding into a red giant. But to the universe, Earth is not the center of the disaster. Our planet is a tiny, warm rock inside a machine, older and colder than instinct can understand. The deeper question is not how life on Earth ends. The deeper question is how reality itself dies. Does the universe freeze, collapse, tear itself apart, or suddenly change its own laws? For centuries, that question belonged to poets, philosophers, and religions trying to imagine the final darkness. Today, it also belongs to telescopes, particle accelerators, supercomputers, and equations written with terrifying precision. We do not know the final answer, but we have found several possible doors to the end. Behind each one is a different kind of cosmic death. Some are slow enough to make eternity feel exhausted. Some are violent enough to destroy matter from the inside out. And one of them may already be moving toward us, with no possible way to see it coming. To understand why the universe can die, we first need to understand why it exists this way at all. We have to go back to the moment the trap was set. About 13.8 billion years ago, the universe began expanding from an extremely hot, dense early state. The Big Bang was not an explosion inside empty space, like a bomb going off in a dark room. It was the expansion of space itself, carrying matter, energy, and time into a new cosmic story. Every region of the young universe moved away from every other region as space stretched and cooled. For a long time, scientists thought the ending might be almost beautifully simple. Imagine throwing a baseball straight up into the sky. At first, it climbs fast, powered by the force of your throw. Then gravity begins to win. The ball slows down, stops, and falls back toward Earth. For decades, many cosmologists thought the universe might work in a similar way. The Big Bang sent everything flying apart, but gravity was always pulling everything back together. Every galaxy, every star, every planet, and every cloud of gas added to that invisible pull. If enough matter existed, gravity could eventually defeat the expansion of space. The universe would slow down, stop growing, and reverse direction. Galaxies would rush back toward each other. Stars would collide, black holes would merge, and the entire cosmos would collapse into a final furnace. This ending was called the Big Crunch. It had a strange kind of comfort. A universe born in fire would die in fire, and maybe even begin again. It was neat, symmetrical, and almost mythological. Then, in the late 1990s, the universe broke that story. Astronomers were studying distant exploding stars, trying to measure how much cosmic expansion was slowing down. Those explosions acted like markers across deep time, showing how the universe had changed while their light traveled. The expectation was simple: gravity should be putting the brakes on expansion, but the data kept pointing to the same impossible result. The universe was not slowing down. It was speeding up. The baseball was not falling back. It was accelerating upward into the dark, as if empty space itself had started pushing it away. Something invisible was overpowering gravity on the largest scales of existence. Scientists gave that unknown driver a name: dark energy. The name sounds like an explanation, but it is really a label for a mystery. Dark energy is whatever causes the expansion of the universe to accelerate. It appears to make up most of the universe's total energy budget. Yet we cannot hold it, isolate it, or point to a machine and say, "This is dark energy." We only see what it does. It stretches the distances between galaxies. It turns the universe into an ocean where every distant island slowly drifts beyond reach. And because the fate of everything depends on dark energy, its mystery is not just scientific, it is existential. If dark energy remains steady, the universe may die in a long, freezing fade. If dark energy grows stronger, it may eventually tear reality apart. And if the vacuum itself is unstable, the universe may not need to wait for either ending. The first possible ending is the quietest, which makes it feel almost merciful at first. It is called heat death, but the name is a trap. The universe does not burn to death. It runs out of differences. No final explosion, no cosmic scream, no giant wall of fire moving through space. Just a future where every engine slowly loses the ability to turn. The process begins with distance. As space expands, faraway galaxies are carried farther and farther from us. Eventually, many of them cross a cosmic horizon where their light can no longer reach anyone here. They do not disappear because they die. They disappear because the universe stretches the road between us faster than their light can travel. One by one, the night sky loses its witnesses. Future civilization may look upward and see almost nothing beyond its own galactic neighborhood. The rest of creation would still exist, but it would be sealed behind distance itself. The universe becomes a collection of lonely islands, each surrounded by an ocean that cannot be crossed. For a while, our own island still survives. The Milky Way and Andromeda merge into one enormous galaxy filled with old stars. It may look alive for a long time, but the death has already begun. New stars need cold gas, and that fuel slowly runs out. The brightest stars die first, burning fast and leaving behind collapsed remnants. Smaller stars keep glowing for ages, like the last candles in a cathedral after everyone has left. But even those candles are not eternal. One by one, the stars exhaust themselves. The sky stops being a city of lights and becomes a graveyard. White dwarfs cool into black embers. Neutron stars sit in the dark like crushed fossils of ancient explosions. Black holes remain as the last great monsters of the universe. For a while, black holes look like the final survivors. They swallow light, bend space, and hide their interiors behind borders nothing can cross. But even they are living on borrowed time. According to Hawking's calculations, black holes should slowly leak radiation into the emptiness. The process is almost absurdly slow, but eternity is patient. Over unimaginable spans of time, the black holes shrink. Smaller ones vanish first. The giants last longer than stars, galaxies, and almost every structure we know. But eventually, even the giants die. The universe loses its final engines. Then comes the deeper question. What if matter itself is not permanent? Some theories suggest protons may eventually decay, although we have never observed this happening. If that is true, atoms are not eternal bricks. They are temporary agreements. Planets, oceans, bones, dust, and dead stars would all dissolve into simpler particles. Nothing solid remains solid forever. What is left is not a battlefield. It is a thin, exhausted fog, spread across distances so vast that distance itself becomes meaningless. No stars, no planets, no chemistry, no memory, no place where anything complicated can begin again. This is maximum entropy. Not chaos in the exciting sense, but something worse. Sickness. Life needs differences, hot and cold, fuel and waste, order and collapse. A body lives because energy can move. A fire burns because heat can flow. A brain thinks because tiny physical differences can become signals. But in heat death, the universe becomes too even to do work. Energy still exists, but it is spread so thinly that it can no longer build anything. Time may continue as a number, but the story of time is over. There is duration, but no transformation. There is a future, but nothing left for the future to do. And then, inside this dead eternity, physics offers one last grotesque possibility. If time stretches forever, even impossible accidents start to become tempting. Random fluctuations could, in some models, briefly arrange particles into something horrifyingly specific. Not a star, not a planet. Mind. A conscious brain could flicker into existence inside the void. It might believe it had a childhood. It might remember a mother, a language, a home, a fear of dying. It might even believe it is you, but none of it would be real. The memories would be fake, assembled by accident from the noise of a dead universe. For one instant, this brain would wake up inside absolute emptiness. Then it would dissolve before it could understand that it had never truly lived. This is the Boltzmann brain. A nightmare where consciousness survives only as a random glitch in a universe that has forgotten how to create life. Heat death is terrifying because it does not kill everything at once. It waits until stars are gone, matter is gone, motion is gone, and meaning has nowhere left to happen. It is not the universe exploding. It is the universe becoming so empty that even death has nothing left to destroy. But this ending depends on one assumption. It assumes dark energy stays calm. If that assumption is wrong, the universe does not fade away. It gets torn apart. This brings us to the Big Rip. The Big Rip is not the standard fate of the universe. It depends on a hypothetical form of dark energy, often called phantom energy. In this scenario, dark energy does not merely continue pushing galaxies apart, becomes stronger as the universe expands. The more space grows, the more destructive the expansion becomes. At first, nothing on Earth would seem unusual. People would still go to work, argue online, fall in love, and make plans for next year. The sky would still contain stars. The sun would still rise. Gravity would still hold your body to the ground. But on the largest scales, the universe would already be coming undone. Galaxy clusters would be the first to lose the fight. These vast families of galaxies, barely held together by gravity, would begin to separate. Then the pressure would move deeper. Galaxies themselves would start to unravel. Stars at the edges of the Milky Way would no longer remain bound to the galactic center. They would drift away into the expanding darkness like sparks thrown from a dying machine. The galaxy would not explode all at once. It would be pulled apart thread by thread. Then the destruction would reach the scale of solar systems. The sun's gravity would lose its grip on the planets. Earth would become an orphan world, no longer following the path it held for billions of years. The moon would slip away from Earth. Tides would lose their ancient rhythm. The familiar architecture of the solar system would become meaningless, but the Big Rip would not stop with orbits. As phantom energy intensified, Earth itself would lose the battle against expansion. Gravity would no longer hold the planet together. The crust would fracture. The mantle would tear open. The planet would be ripped apart by the expansion of space inside and around it. Then the disaster would become smaller than worlds. Molecules would fail. The electromagnetic forces holding atoms together would be overwhelmed. Chemistry would end. Then atoms themselves would be torn into their components. At the final stage, even the structures inside nuclei could no longer remain intact. In the Big Rip, the universe does not fade into darkness. It is dismantled. First the clusters, then the galaxies, then the stars, then the planets, then the atoms. It is not death by emptiness. It is death by expansion becoming stronger than structure. The heat death is an ancient candle burning down to nothing. The Big Rip is the hand that tears the candle, the flame, and the room apart. Still, both endings share one psychological comfort. They belong to the far future. They happen on timescales so enormous that the human mind turns them into philosophy. You can hear about them, feel disturbed for a moment, and then continue your day. But the next ending does not offer that comfort. It does not require stars to die. It does not require dark energy to change. It may depend on whether the vacuum beneath reality is truly stable. This is where the Higgs field enters the story. In 2012, physicists at the Large Hadron Collider discovered the Higgs boson. The discovery confirmed the existence of the Higgs field, an invisible field filling all of space. This field helps elementary particles acquire mass. Without it, the familiar structure of matter would not work the way we know it. But when scientists measured the Higgs boson, the numbers raised a strange possibility. Our vacuum may not be perfectly stable. It may be metastable. That means it could be stable enough to last for an almost unimaginable time, but it might not be the deepest, safest state that physics allows. Imagine a stone resting in a shallow pocket on the side of a mountain. It can sit there for ages without moving. From a human perspective, it looks safe. But lower down the mountain, there is a deeper valley. If the stone somehow reaches that valley, it will not return to its old position. Some calculations suggest our universe may be like that stone. It may be sitting in a false vacuum, not completely doomed, but not absolutely secure. Quantum mechanics makes this more unsettling. In the quantum world, a system does not always need to climb over a barrier. With tiny probability, it can tunnel through. If the Higgs field ever tunneled into a lower energy state, a bubble of true vacuum could appear. That bubble would not be an explosion in space. It would be a change in the state of space itself. Inside the bubble, the laws that allow our kind of atoms in chemistry might no longer apply. Ordinary matter could become impossible. The universe would not be damaged. It would be edited. The bubble could begin anywhere. It could form in a remote cosmic void far beyond every galaxy we can see. It could have formed billions of years ago, with its edge already racing toward us. Or it could, in principle, form somewhere much closer. The terrifying part is not that this is likely tomorrow. The terrifying part is that if it happened, no warning could arrive first. No telescope could save us. No shelter could protect us. No civilization could outrun it, because the rules needed to run would be rewritten. Vacuum decay is the cleanest apocalypse imaginable. No fireball in the sky, no final war, no slow extinction. Just a new state of reality expanding through the old one. This is why the universe feels less like a solid structure and more like a temporary agreement. A fragile balance between fields, particles, forces, and constants. We live inside that balance. We trust it every second. Every heartbeat assumes the laws of chemistry will still work. Every breath assumes oxygen will still behave like oxygen. Every memory assumes atoms will remain atoms long enough for a brain to hold a thought. And yet physics allows us to ask whether that agreement is permanent. Some scientists search for ways around these final endings. Maybe the universe is cyclic, passing through death and rebirth on unimaginable scales. Maybe a collapse could lead to another expansion. Maybe our universe is one region inside a much larger cosmic structure. Maybe there are hidden dimensions, other domains, or deeper laws beneath the ones we understand. These ideas are fascinating because they make destruction feel less final. In some models, a cosmic ending may become a reset, but a reset universe is not the same as a saved universe. Even if reality begins again, this version of reality may still be erased. Our planets would not survive. Our history would not survive. Our names, languages, cities, and memories would not pass through the fire untouched. A new beginning may be possible, but it would not be our continuation. That is the part our brains resist. We can accept that we will die. We can accept that civilizations rise and fall. But the death of the universe attacks something deeper. It attacks the stage itself. Every human ambition assumes there will be a future for it to echo into. We build, learn, record, preserve, and imagine that something will remain. But cosmology tells us there may be no eternal archive, no final witness, no permanent monument, no cosmic memory holding everything that ever mattered. So why should anything matter? If every star goes dark, if every atom decays, if reality itself can change, why care? The answer is not hidden in some comforting loophole. The universe does not owe us permanence. It does not promise that meaning must last forever to be real. A song matters even though it ends. A life matters even though the body that carries it is temporary. A civilization matters even if its monuments cannot outlive the final stars. Permanence was never the price of meaning. Maybe the strangest fact in the entire story is not that the universe can end. The strangest fact is that the universe produced something capable of knowing that. It forged elements in dead stars and scattered them across space. It built planets from dust, oceans from chemistry, and living cells from ancient atoms. Then, on one small world around an ordinary star, matter became aware of itself. The universe made brains that could calculate the age of stars. It made eyes that could collect ancient light from galaxies billions of years away. It made hands that could build machines powerful enough to detect hidden particles. It made a mind capable of asking whether the vacuum under reality is stable. That does not cancel the darkness. It makes the brief light more astonishing. We are not outside the universe, watching its tragedy from a safe distance. We are the universe, arranged for a moment into something that can understand tragedy. Every atom in your body belongs to the same cosmic story as galaxies, black holes, and dark energy. Your thoughts are not separate from physics. They are physics becoming aware of itself, and that awareness may be temporary. It may disappear when the stars die, when space rips, or when the vacuum changes state. But temporary does not mean worthless. It means rare. It means fragile. It means this moment is not guaranteed by anything. The universe may end in silence, violence, collapse, or a sudden rewriting of reality. We do not know which ending waits at the far edge of time. We only know that the stage is not eternal. The laws feel solid because we were born inside them, but on cosmic scales, even the laws may have a history. And if they have a history, they may also have an ending. That is what makes existence so unsettling. Not that everything dies, but that everything exists at all. Against all the coldness, all the entropy, and all the possible endings, the universe woke up here. For one brief moment, it looked back at itself through us. It measured its own expansion. It discovered its own darkness. It calculated the possible mechanics of its own death. The universe may never remember us. It may not preserve a single trace of our names, our fears, or our dreams, but it produced us. And for a brief, impossible, shining moment, we got to understand it. In a universe destined for darkness, that moment is not small. It is everything.